Okay, let's do this. So, first thing, we had I'll remind you of the first, get this just right. I'll remind you of the first few weeks, but I'm in the lecture channel on Discord. If you see me looking at my phone, that's what I'm looking at. And if you have any questions, feel free to hit me up in there. We do have a TA in here. We have a TA for, should be every lecture, so they can answer your questions in chat, or I'll answer them, or do the old-fashioned raise your hand. Always still works. We had a few questions. Yeah, I'm getting my Dr. Hertz influence with the shirt here. A little lower. There were a few questions in chat at like 49 minutes into the lecture I didn't see until after. So I want to clear up a little bit of a confusion with one of my examples. When I was talking about the phone lines where you're taking up like a whole line when you're calling, that's like old days that none of y'all will remember. I'm kind of dating myself a little bit with that one. And that wasn't affected by DSL. When we got to DSL, that was definitely not an issue. With dial-up internet, that's where you would actually use the phone line, effectively make a phone call to your ISP, and then you would use the phone lines to connect. And then when somebody picked up the phone, you lost that connection, and it wouldn't, you'd get disconnected. But what I was talking about was even before dial-up, when you actually had community lines, you had shared phone lines with your neighbors. So like you and, I'm just making up numbers here, but like you and 10 neighbors might have 3 total phone lines. And if 3 of your neighbors are making phone calls, you can't make a phone call. So eventually we got a line or more often 2 lines for every single house, and then we no longer had that issue. But we would still have the dial-up issue if you're using one of the phone lines for your dial-up connection and somebody picked up the phone, they would take over that connection. Yeah.
Wait, so they actually transferred the data, the ISP actually transferred the data through the phone line?
Yep. Yeah, that's what the first early days of the internet were, and it sucked. It sucked a lot. But that's what a modem does. So a phone call, you make a phone call, it's an analog transmission. These days it's actually digital. But a regular old-fashioned phone would be an analog signal over the copper at that time. And what a modem does is takes a digital signal and turns it into an analog signal. So it takes a digital information and sends it over an analog channel. And that's what the modems did. So the modem, your modem on your end and a modem on the ISP's end would take digital, translate it into analog, send it over the analog phone line, and then their modem would decode the analog back into digital, and then send it to the internet, which hopefully wasn't using phone lines at that time. But our connection to the ISP would use phone lines, and then if you had a cable connection, like if you had cable TV, a lot of this y'all probably don't remember at all, do you? You weren't around for any of this, but if you had an actual cable connection to your house, like cable TV and stuff, then they came out with DSL, which would use your cable connection instead of your phone line. And then the speeds were much, much faster. That was made for communicating in a digital signal. So then we were able to communicate a lot faster with DSL. And now, since people are using the internet and not just watching cable TV, all the cables have been replaced. Most places we have fiber now, and all kinds of huge bundles of fiber and stuff like that. So now speeds are kind of up there to fit our needs of the day. But in the old days, it was, well, you have a telephone line already running to your house. Let's try to use that to build out the internet to access more people. Well, you already have a cable TV cable going to your house. Let's try to use that line and communicate internet stuff over it. Now the infrastructure is built with the internet in mind, so we have high speeds now. But back in the day, the ISPs were just doing whatever they could to try to get internet to us. But yeah, what I was talking about was way back before any of that, which was how the phone lines work, where you actually get a line, which is a connection, which did interfere with the modem, the old dial-up stuff, but definitely didn't interfere with DSL. So even in the dial-up days, DSL, whatever we were using, the internet was always packet switching. the internet, when it was dial-up, did have a little bit of the infrastructure, since it was using the phone line infrastructure, had to have that connection over a persistent connection, but it was still packet switching when it got to the internet. When it got to the first internet router, it was always packet switching. It was a very inspired decision way back in the early days of the internet to have it be packet switching instead of, I forget what the alternative is even called. The other question in chat was, how does it decide what path to take through the internet? That question I'm not going to attempt to answer. It's very complicated, and you have to take modern networking concepts. You'll learn all kinds of different routing protocols. They get fairly complex, have to do with routing tables. What I'll talk about is what's on this slide, and that's where I'll leave it. Is each router has a forwarding table, which is specifying what we call the next hop is for a packet. So a router is going to have a queue of packets, and each time it gets a packet, it's going to look at the IP address, look up that IP address in its forwarding table, and figuring out which router it should send that packet to. So each router only knows about its neighboring routers and just where to send each IP address to. And usually it's only going to read a prefix of the IP address. If the IP address, the first number is a certain number, it's going to send all those packets to a certain router. The first number is another one, it'll send it to another router. And it's just going to use these routing tables, these forwarding tables to decide. Now, how to update those routing tables, that's a modern networking concepts question. They'll tell you how routers update those tables and how those changes propagate through the internet and how all that stuff works. Gets pretty complicated. Gets interesting, too, if you're into that kind of thing, though, if you're into how things are transported. So each router of the internet only knows the next step. A router on the internet, that's all it does is what I just described. Gets a packet, reads a packet, looks at the destination IP address, and sends it to the next router of the internet, and then it goes to the next packet in the queue and does the same thing. That's it. This makes the internet very unreliable. So for example, what happens if a router sends that packet to the next router that, according to its forwarding table, sends it to that next router, but actually there was a cable that was severed in that connection, and that router that it sent it to isn't actually there. It's not connected, or it's powered off, or maybe it's just malfunctioning or whatever, where that router that it sent that packet to isn't working. There's nothing built into the internet to detect or correct or fix that issue. There's nothing built into the internet to fix that, to resolve that. So in the internet, dropped packets are just a way of life. These routers are meant to be fast, efficient. They're not meant to be accurate, and they're not meant to ensure that your data is going to make it to its destination. The internet just doesn't do that. The internet is unreliable. And when I say the internet, I mean IP, the internet protocol, which is the protocol all the routers are using. That is unreliable. So we don't like that. What was the course? Whenever I read what is the course website again, I hope it's a joke. I guess not. Maybe you just skipped Monday or whatever, but I hope it is. So we need to fix that. We don't like this idea that our data just might not make it to its destination. That's not a good feature, and if that was it, like that's how the internet worked and nothing else, we wouldn't really use the internet, I don't think. It wouldn't be as popular as it is today if it was just unreliable. Sometimes people didn't get your messages that you sent them and stuff. That's not great. So TCP to the rescue. What TCP does is say, okay, the internet's unreliable, but let's make it reliable. Let's force it to be reliable. This is what TCP gets for us. TCP builds some extra information to be able to correct for dropped packets, among other things. It does other things for us too, but that's the big reason why it's essential. So with TCP, instead of just sending information to a destination IP address, before any information is sent, we're going to do what's called a three-way handshake. So this handshake is going to establish a connection between two devices on the internet. So to do this, the device that wants to connect is going to send a message to whatever device it's going to connect to. In this diagram, it's labeled as client and server, which is the most common use case. But just any two devices that want to create a TCP connection, this would apply to. You send a sync message, which is nothing fancy. It's just a random number. That random number we're going to call M. The server, now I already backed out on that. But the other device is going to get that number M, and it's going to do something very magical to it. It's going to add 1. It's going to take that random number M, it's going to add 1 to it, and it's going to send it back to the other device as the acknowledgement M plus 1. And it's also going to send its own random number as another sync message, N. That first device is going to add 1 to N and send that back to the other device, to the device it's connecting to. So we have three messages being sent, random number plus N plus 1 plus another random number, and then that random number plus 1. So this isn't really doing much. We're just adding 1 to random numbers, like nobody cares. But what this does is confirms, each side of the connection confirms that the other side speaks TCP. The other side understood that, hey, I'm sending you a random number. It was able to decode that message, decode the bytes that were sent over the internet, understand that it represented a number, was able to do a mathematical operation on it, encode that new message, and send that new message back over the internet. So it doesn't mean much to us. They added 1 to random numbers, big deal. But there was a lot going on that verifies that to either side that the other side speaks the proper protocol. That each side understands what TCP is. They understand that this is a TCP connection and that we can speak in TCP from now on. This third step of the handshake usually comes with some extra data. That's usually, okay, whatever reason I was creating this connection for, I'm going to send some data over that connection, which in our case is mostly going to be HTTP requests, which we'll start talking about today. This is also going to include some metadata about the communication that's about to occur. So last time we said packets are limited size. Somebody asked in chat what that size is. I don't know off the top of my head. I think it's on the order of kilobytes, but I don't know the exact number. I think it's different based on different routers, too. I forget. I'll pawn that one off to modern networking concepts, too. But these packets are pretty small. Like, you're not going to be able to download a movie with just one packet, for sure. So when you want to send a large amount of data over the internet, you have to split it into multiple packets. And those packets might find different routes through the internet. As these routers are updating their forwarding tables, like these packets might find different routes through the internet. Some of them might not make it to their destination. Some of them might make it. And some of them might arrive out of order also. So if a router updated its routing table and found a more efficient path through the internet while you were sending these packets, some later packets might arrive before some earlier packets, for example. So a lot of stuff can happen when you just send a bunch of packets throughout the internet. TCP addresses this by giving each one of those packets a routing number and communicating that information. The first thing, hey, I'm about to send you, say, 5,000 packets. That's what the receiver gets. I'm going to send you 5,000 packets. And then you send all those 5,000 packets with routing numbers 1 through 5,000, and then the receiver now knows, hey, I'm missing packet 436. Well, now it can send a resend request. Say, hey, look, I got a lot of those packets, but I'm missing a couple. Can you resend these ones? Then you resend, and if you still don't get them, send another request. There are timeouts and all kinds of algorithms to figure out the best way to do that. And since the receiver knows how many packets it was expecting, say you're expecting the 5,000 and you only get the first 4,000, you know that you have an incomplete transmission, and you can say, hey, something happened, we cut out at 4,000, can you send me 4,001 through 5,000? So we're still accepting dropped packets. Dropped packets happen all the time. That's just a fact of life. But TCP is saying, okay, let's add a layer of protocol on top of this, so when a packet is dropped, we have a method of recovering that dropped packet without just resending the entire, if you're sending a 10 gigabyte MP4 or something, we don't want to resend the whole thing. Let's have a protocol that just resends the pieces that we're missing and then reassemble it at the other side. Now, since we have all of our packets numbered, we can also sort them. You got all your packets, you sort them by their sequence number, you reassemble them all, and now you have the entire message that was being sent over the internet. Reliably, some of it might have gotten there unreliably, but we're going to request resends. Everything's going to get there eventually. So what TCP does is gives us a reliable connection over an unreliable network, or an unreliable, gives us reliable communication over an unreliable system. We'll go with that one. I don't know why I had it in my head and then I forgot by the time I got to the end of my sentence again. But yeah, it gives us reliable communication. That's the important thing. So TCP, IP, you usually hear these two together. IP is how packets are routed through the internet, and TCP is giving us that layer of reliability so we can actually get the information that we sent. Yeah.
Okay. How does let's say like you want to download an MP3 to your phone or whatever, or a movie or something. How do you know if a packet is missing? Like, how do you know if it was dropped or if it just hasn't been sent yet? If they're all being sent out.
So this is the beauty of it. So the question is, if you're downloading something, how do you know if a packet was dropped or what? The beauty of TCP is we don't need to know. So by the time the information gets to us, the user, TCP already did its job. And we just get the information.
But how does TCP, like, when a packet is dropped, like if packet 4000 gets dropped, how does the resend, what is the resend procedure?
So it has a lot to do with timeouts. I don't know all of the specifics of it. I forgot some of the details of it. But it's based on timeouts. So if it gets all these packets, but one of them is missing, it'll wait a certain amount of time. The TCP protocol will, you'll wait a certain amount of time and then request the resend. And then there's another timeout after that, because what if the resend request itself was dropped? It's going to have another timeout. It's going to wait a certain amount of time and then request a resend again, and keep doing that until some failure state where it's going to say, okay, I give up.
And then the client gets packets, they like any confirmation for each packet.
Does it? I don't recall off the top of my head whether there's a confirmation. My guess would be that the lack of a resend request would be taken as a confirmation, but I'm not 100% on that one. No problem. Again, I'll pawn that off on my networking concepts. My next slide might even pitch that. Oh, in a couple. So TCP, everything I talked about, the three-way handshake, IP, TCP, IP, we're going to take all that for granted in this course. You're going to use a library in your language of choice, which, by the way, I recommend Python. I'll say that early and often. I recommend Python for this course as it's set up right now, at least. You can use whatever you want, but most students started using Python, and like back when I first started teaching this course, and then more of my lecture examples were built in Python to hit the majority of students. And then that in future semesters just got more students to use Python because my examples were in Python. It kind of just gravitated towards that. So I recommend Python. I'll do the most lecture examples in Python. And I think it's the easiest language to work with in this course. So you can focus on the content of the course without fighting your language too much. For example, I've seen some students try to use Java, and they end up fighting Java more than thinking about the course content. But anyway, in your language of choice, you'll import a TCP socket library, which is going to start a TCP server, which TCP clients can connect to. The library will do the three-way handshake and everything. The library is going to hide all of the details that we've talked about in this slide deck. And from your perspective, you're going to get TCP connections, and those connections are going to send you bytes of data. And when you read the bytes of data, you don't have to worry about drop packets or anything. TCP already did its thing. By the time you get the bytes, you just read bytes off of the TCP socket stream and then handle those bytes according to everything that we learn about in this course. That's why I start TCP on day one, which I might have to just make these slides shorter so I can fit it all in day one, but that's fine. Because it's not really part of the course content that I require you to understand. Beyond this, every detail that I talk about in lectures will be something that you actually have to code in your projects. So here's my pitch, my official pitch for modern networking concepts. There's tons of more information about this, about TCP, IP, UDP, all kinds of good stuff in modern networking concepts. For the rest of this course, we're going to focus on layers above this in the network stack. We're going to focus on application layer and higher. It's not strictly true, but whatever. We're not going to worry about this low level of communication, but CSE 486 lives in this territory. So if you want to get the lower level communication, that course would be the one to take. If you want to focus on the higher level, like what do we actually do now that we have a reliable connection over the internet, that's what we focus on in this course. But we take TCP IP for granted in this course. Aside from the slides I just showed you to give you a little bit of background of what's going on when you import TCP socket servers, that's it. That's all we need to know about it. Now we want to get into today's content, which leads into the rest of the course. Sending these numbers via the Oh, I missed a lot of chat. I think I might have missed that. Saying these numbers via I assume, I missed one thing on TCP I want to talk about actually. The sequence numbers, the three-way handshake, those are critical to TCP. But also, what I forgot to mention, port numbers. Whenever you hear about port numbers, that's a TCP thing. I think UDP also adapted port numbers, if I'm not mistaken. But whenever you connect to an IP address, that's the IP, the Internet Protocol. And if you connect to that address at a specific port number, that port is going to be a TCP thing. So TCP also allows multiple connections between devices. So you can have multiple connections with multiple different servers simultaneously. And when you get that information, when one of those connections is sending information back to you, it sends it to you at a specific port number. So your operating system knows how to route that traffic and knows to route it to the appropriate process running on your machine. Or else you would just have one connection with one device at a certain IP address, and we wouldn't know what to do with information coming in. Yeah.
So a laptop would have like one IP address, but could have multiple TCP ports?
Yep. Mm-hmm. For example, you can have multiple tabs open in your browser. Each tab is going to have at least one TCP connection to make that request to the website. Did you have a question? Oh, sorry, I thought you did. They have specific IP addresses and port numbers. So when you go into your code and you create your first TCP server, that server is going to listen for those three-way handshakes for the first sync message. It's going to listen for those. When you create that server and tell it to start listening for connections, you'll specify a port number. And then whenever somebody wants to connect to you, they're going to have to connect to you on that specific port number so that your operating system knows to send it to your program that's listening on that port number, and then your program will handle all communication on that port. And anything for a different port is going to be routed either somewhere else or nothing's listening on that port, and it'll just do nothing. But you'll specify the port, and everybody who connects to you has to know that port number. Using TCP, you can't just connect to an IP address. You have to connect to an IP address and port number. That's how you can have multiple connections. Like on the server side, we want more than one user. So we have multiple TCP connections to their specific IP and port, but they're all connecting to us. Oh, I said that kind of weird. But they're all connecting to us on the same port number. Yeah, why would anyone need UDP? I'm a little behind that conversation. I'm just going to stare at my phone, though. If there's something, if there's a question or something for me in there, at me in the chat. So we have the physical internet. This is where we came from in those slides, the last slides. We have the physical internet, which is a lot of big cables and some small cables connecting us physically throughout the internet, and then a little bit of Wi-Fi for the last hop. We have IP, which is how are we going to route things through those wires. We have wires. How do I send something to a specific person or a specific device? And then TCP, which is how are we going to send something reliably over those wires. So we have the whole setup of the internet where we can reliably communicate with anybody, practically everybody on the planet. We can reliably communicate. The next question is, the hell are we going to do with that? And this is where we're going to talk about HTTP. Did you have?
I was going to ask. You answered.
Oh, cool. So this is where HTTP is going to come in. In HTTP, we will talk about at length, extensively throughout the whole semester. This is your first intro to HTTP. This is like the protocol of the web as opposed to the internet, of websites and all that good stuff. HTTP is really what all of that is built upon. So whenever we have a packet, we can only send IP packets over the internet, but when we send those packets, we're going to have multiple layers of headers being sent in those packets. So we'll have the IP headers. These are the only things that the routers of the internet are going to read. This is how they're going to decide where to send this packet. Once that packet reaches its destination machine, that machine's operating system is going to read the TCP headers. It's going to throw away the IP headers. Those are done. IP did its job. It's going to read the TCP headers and do any TCP stuff that it needs to do. No, I misspoke there. The operating system is going to route based on the TCP headers, and then the program is going to read the TCP routing numbers and stuff and reassemble it. And then once we get the packet, we get this information. After it's reassembled using TCP, all that stuff is all done for us. We're going to remove these headers. Well, we don't. They're already removed by the time our code gets to read that information. And we're going to read the rest of the stuff, which the first thing we're going to read, the first thing we're going to see in our code, in your code when you start coding the homeworks, is going to be the HTTP headers. So what we'll actually get when we're using these TCP connections are going to be HTTP messages. So let's talk about what HTTP even is. So this is what we call an application layer protocol. It means our applications, our software that we're writing, our software cares about this protocol. Where TCP and IP, our software doesn't really care about that protocol. Our applications don't. Those are at lower levels in the system. This is the first one that our code cares about at the application layer. It almost always uses TCP. Having an HTTP server that's not using TCP doesn't make sense to me. If my server is sending the the HTML for a website, I don't want to drop a packet in the middle of that and miss some of my code. I want you getting the whole website with the full accurate experience. I'm going to use TCP to make that reliable. I say almost always here just because I always like to hedge my bets, but I couldn't see using HTTP without TCP unless you use some other reliable protocol other than TCP, which I think might start. I don't want to go down that road. You need a reliable connection. You need reliable communication. So we're going to do a quick overview of HTTP. I'm going to talk about quite a bit of details about HTTP today, and then over the next few lectures, I'm going to focus on each one of those details in a bit more depth. But today I just want to give you an overview of what HTTP even is and how it works. And then starting Friday, we'll get into some juicy details that'll help you get started on homework, and I'll definitely release the details of the homework by Friday of homework 1, if not earlier. So, and homework 1 is a lot of, I don't want to say basic, but like intro HTTP, working with HTTP and TCP and Docker, which is next week's stuff. So HTTP is a protocol just like IP and TCP are a protocol, and I just want to take a moment to hopefully dispel some magic here, which should be a tagline for this course of what we do here is dispel magic. The internet, before you really study the internet and figure out how it works, seems like magic. I want to dispel this magic and make you understand what is going on when you go to a web page and when you use some forms, you log in. I want you to understand how all that stuff works, and there's really no magic behind it. One thing that seems like magic are protocols, IP, TCP, HTTP, the 3 that we're talking about already. But a protocol is just an agreed-upon way to communicate, an agreed-upon way to do things. Communication in our applications here, being a web course. But HTTP is just a set of rules that says when you send information, send it in this format. And if you're sending things in that format and the other side studied the same protocol and wrote their code to parse that format, we can communicate effectively. But it's just a format of where to put information. Because over the internet, we have wires. We have copper wires that can either send high electricity or low electricity. We have fiber, which can either send light or dark. It's all binary. It's all ones and zeros. That's the only thing that can be sent over the internet. It's all digital. We have no analog signals. It's all digital. It's digital protocols that we're talking about. So what these protocols do is say, send us ones and zeros in this very specific sequence, and then we'll be able to communicate effectively. So with IP, when I showed the headers slide, do I have that here? Forgot I wanted to talk about that. No, I don't. So like when I had the header slide, I'm not going back to the other slide deck. All that is saying is when you send an HTTP or an IP message, the first 4 bits, the first 4 ones and zeros are going to be the version of IP, in these days either 4 or 6. It's going to be the version of IP that you're using. Then the next however many bits are going to be some other information, the next, et cetera, and then you have the IP addresses. These, in this sequence, this chunk of bits is going to be the destination IP address, and then the source IP address. It's all just saying, you send me ones and zeros, and I'm going to expect all the information to appear in this order with fixed width number of bits for each piece of information, so I know exactly which ones and zeros represent the information I'm looking for. And that's it. A router in the internet gets a bunch of ones and zeros, and it knows exactly where to look, which ones and zeros mean the destination IP, and then it knows where to send that packet. And there are ways to say this is the end of the packet. It knows when to stop reading that packet and when the next 1 or 0 represents the start of the next packet. And that's it. That's all protocols are, is saying, okay, this is how we're going to communicate because the internet's only ones and zeros. This is how we're going to make those ones and zeros make sense. So we have the IP headers, which are just bits in certain orders. TCP, same thing, bits in certain order that represent the things like the port number and sequence numbers and things like that. And then by the time we get to HTTP, we're still just working with ones and zeros. So we have to make sense of the ones and zeros that we receive. Now, luckily for us at HTTP at this level, we can end up, for now, until homework 2, we can treat these as strings. They still are ones and zeros, but we're going to decode them as strings and make sense with them using our string encoding protocols, and not have to think at too low of a level yet until we start getting further in the course. But we need to make sense of those ones and zeros that are being sent over the internet. And HTTP is just another protocol that's going to help us make sense of that information. But all it is ones and zeros over a wire or over a fiber connection. So HTTP, just a set of rules to make sense. If our servers are speaking HTTP properly, and our browser is speaking HTTP properly according to the protocol, we'll be able to effectively communicate using this protocol. HTTP is a request-response protocol. So what happens is you're going to run your TCP server, which you're going to write code on top of that to be an HTTP server. And when you get a TCP connection established and that TCP connection is sending you information, you're going to parse the HTTP request according to the protocol, and then send back an HTTP response. HTTP, you can't send information to the client without getting a request first. You get a request, you send a response. You get a request, you send a response, and that's it. And that's what we build the whole internet on top of, is this request-response idea. So when you get one request, typically it's going to be a request for your home page or some HTML if they're not at your home page, if they navigated to something else. You're going to send the HTML for that page. It's all you respond with. When you're writing your code for your server, you're going to have some code that says, if they're requesting my home page, here's my HTML, and that's it. Now, in most cases, that client is going to have to get more information from you. It's going to need your CSS and JavaScript, assuming that you have CSS and JavaScript on the page. It's any images that you have on the page, any other multimedia. It's going to need all of that information. And you know that. With your server, you know that when they request your homepage, you know that they need a lot of information, but you're only going to send your HTML, and that's it. This trips up a lot of students, this idea that you know that they need more information, so you want to send it all right away. Don't write your code like that. It's a request-response protocol. You get a request for the HTML, you send the HTML and the HTML only. And then what the client is going to do, what your browsers do whenever you visit a web page, is it parses that HTML and looks for any other information that HTML requires. It's going to have an image with a source property that's going to give some URL of where you can find that image, and it's going to say, oh, looks like I need this image, and it's going to make another request to your server and say, yo, I need this image, and your server's going to be, okay, here it is, and you respond with just your image. Then it's going to make another request. Oh, looks like I have some CSS that I need. Hey, can I get that CSS? And you're going to say, yep, sure, here's the CSS. Oh, I need that JavaScript. Okay, here's that JavaScript. And it's going to make multiple requests to your server. So when you're writing your servers, you only have to handle one request at a time. You get a request for the JavaScript, you send the JavaScript. You get a request for the CSS, you send the CSS. You get a request for an image, you send the image. And that's it. You don't do anything else. It's up to the browser to figure out what requests need to be made. And you're not even linking those to the same user. The user's going to request all those things, but you don't care that it's that user each time. You don't even remember that it's that user. Some terminology that we'll use, I'll usually use client and front end somewhat interchangeably, but front end is going to be everything that runs in the user's browser. Oh, user also I'll use fairly interchangeably. Everything that runs in the user's browser is going to be the front end or the client. Technically, a client doesn't have to be a browser. You can write code that makes HTTP requests without using a browser at all. So it's not always a browser, but but I will say client. It will always be a client of your server. So client very often. Front end. I talked about this on Monday a little bit. I just took it for granted, the term front end, but it's everything that is sent to the client. So all your HTML, CSS, JavaScript, and multimedia, everything that you're sending to the user, everything that makes it to your browser when you visit a web page, that's all considered front end. Anything that's not sent is considered back end or server. And just to visualize this a little bit, typically when you visit a website, you request the HTML, the server sends the HTML, and the HTML only. HTML only. And then the browser's going to parse that HTML and say, oh, I need your CSS, JavaScript, and images, and those will all be separate requests, and the web server will respond to each one of those requests with the requested information. Then the browser's going to get all of that information once it has everything that it needs. It's going to get all that information and start rendering the page and displaying the page to the human being on the other side of that browser. All right. Any questions now? I missed a lot in chat, so if there's something that needs my attention, let me know. When is a request being made? Is it when you click a link? A request is made when you click a link, but requests are being made constantly. If you go to, you know what, I might do a demo right now. If you go to, I don't know, Google, and go to right-click and go to Inspect Element, or otherwise open up your browser console, you can go to your Network tab and see all of your HTTP requests and responses as you are at that page. I guess this doesn't do too much. Oh, it does a little bit. So I was just sitting here doing nothing, and it made a request. Oh, just made another request. It's making HTTP requests on a regular basis to the Google server, which are failing. I don't know what these are. Maybe ads that are being blocked, it looks like. And if I refresh the page, I can see all of the requests. Lots of requests to load one page. The first one is going to respond with the HTML. And then that HTML said, hey, look, you need all this other information. I don't even know what that is. Needs this, this graphic. Needs all this stuff, which is unreadable because they all went through obfuscators and compressors. But this looks like JavaScript. A lot of requests when you go to a site. So it's when you click a link, you're going to load a new page. When you type an address in the address bar, or just as the page is sitting there, making more requests to the server to do whatever it does. If you have a page that updates without you doing anything, you're looking at like a live feed, and you're constantly getting updates, those are all HTTP requests going back to the server, unless it's using WebSockets, which we'll learn about later. Yeah.
Is the request in the content of the packet, or is it the HTTP header?
Is the request in the content of the packet? You mean the IP packet? Or
The HTTP packet.
the request is, so we haven't talked about the format of HTTP yet. That might answer this question. Like an HTTP request will be like this whole thing, or this whole thing. Is that getting to what you're asking? So the request will be, hey, I need your HTML. Will effectively be what that request is saying. I don't know if that's what you're asking, though. Yeah.
Earlier, you mentioned that when the packet goes through the TCP and IP slips, it removes those links. So does that mean the content of the whole packet is accessible to the internet service providers and all of the organizations which comes between?
Well, I missed that last part. So by the time we get the information, the IP and TCP headers are gone.
Right. So
But
since the content is just below those.
oh, yeah. Yeah, so your ISP, the tier ones, they can see all that information. They can see the HTTP requests. We'll talk about this in depth when we get to homework, the last homework. I guess that's a while from now, so I'll spoil it right now, is we'll encrypt all that so they can't read it. Did you want to, can I go back to that question? Yeah.
Yeah, I was kind of confused. Like requests are packets, right?
So they're not really packets. In the IP sense, by the time we get an HTTP request, that request might have been sent in multiple different packets that were already reassembled by TCP. So by the time we get an HTTP request, it's all reassembled, and we get it as a stream of bytes is how we're going to read the requests.
Okay, but it's the content of those packets that is the request.
Yes. Yep. So below the TCP headers is going to be the actual HTTP stuff.
And the HTTP headers, those just say like this is an HTTP thing.
That will be something we'll talk about at length, actually. 4 minutes. Let me go through some slides and get there. But like this is an example of an HTTP request, and these would all be the headers, and this would be the body of that content. But the headers are a different format than like IP and TCP, where they say the first 4 bits will be this. It follows a very different thing. It's more of string parsing. We'll end up using a lot of string parsing to get that information. This course has been named by one of the TAs, actually, of string parsing the course. We do a lot of string parsing to parse these HTTP requests. So there are a lot of different request types. We'll talk about these, I guess all of these, throughout the semester. For now, we're just going to focus on get and post. And by the time we get to the end of homework 1 content, we'll talk about put and delete as well. Head will come in way later in the course for a very specific application. But we just want to focus on get and post right now. Get, an HTTP GET request, a request of type GET, is going to be requesting information from a web server. This is most things, clicking a link, going to a website, you're just accessing information. Those are all going to be GET requests. A GET request for the HTML, GET request for the CSS, all the examples I've been saying, those would all be GET requests. And if you want to send information to a server, we would use a POST request. A GET request is only going to have headers. A POST request is going to have headers and a body to the request, which is the information that you're sending to the server. Whenever you make an HTTP request, it has to be made to a specific URL. A URL, which I assume you're all familiar with URLs at one level or another. So a URL is going to have this format. Protocol, host, port, path, query string, and fragment are going to be the portions of a URL. The protocol, for our purposes, is going to be HTTP or later on HTTPS, but it could be anything like FTP if you want to transfer files over the internet. You don't have to use HTTP, but for our purposes, mostly it'll be HTTP. The host is going to be the device that you want to connect to. This will be an IP address or a domain name. With a domain name, you'd have to have a DNS lookup to be able to get the IP address. A port, which is going to specify, for our purposes, the TCP port number that you want to connect to, which will be either 40 or 443, whether you're using HTTP or HTTPS, respectively, or any number that we choose. For our homeworks, we're going to use port 8080, which is a common web development port, so you don't always have to use your port 80 on your local host. And then the path, this is the specific resource that's being requested. So index.html, whatever. The query string and fragment are both optional. I think I got rid of all the content that uses these. I don't think I asked you to use these in the homeworks at all. Maybe I will in homework 2. But the query string and fragment are giving extra information on top of the path that helps us deliver a specific resource. Query strings are key value pairs. I don't think I want to focus on it too much. We're running out of time. And if I'm not going to ask you to do it, let's just skip over those. And I at least want to show you the format of HTTP requests. So these are two examples of very stripped down HTTP requests that are similar to what you'll see. This is a request. You always have the request type, the path, and the HTTP version. So you always see the path in your HTTP request. You won't see the protocol, the host, or the port because it made it to you. All that information was already used. And any headers associated with that request. We'll get into the format on Friday. I'm out of time, so I won't bother getting into it right now. But on Friday, we'll talk about HTTP more in depth and talk about how to parse these things. See you then.